everyone, and welcome to my newest video where I talk about design resistance analysis. And in today's video I have an example of a beam-to-beam connection in idea statica. This type of analysis is beneficial when we want to know when a certain connection will fail. And by performing this type of analysis in the software, we will have a coefficient. When we multiply the set of forces with this coefficient, we will have a state of failure of the connection. And also with this type of analysis, we will know which part of the connection will first fail, whether it's the plates, the bolts, or the welds. And we will have some small information about how ductile or how fragile this connection is. This type of analysis is also useful when a client wants to work with the same design, but let's say he wants to do this connection on different places, meaning that different load conditions will apply for the same design. So in this way we will know that if the forces slightly increase, then we are still in the safe zone of the connection. And today's example will be two hollow section beams, and we will load them with 100 kilonewtons tension. I took this value of 100 kilonewtons because it's easily multipliable, and we will see what the margin will be in this type of connection. So I will go now to my idea statica, and right now when you open the software, here you can see a lot of pre-designs given by the software, and here we have the beam-to-beam types of connections, and here we have the hollow section, and here you can see a design that is very similar to the design that we will use today. So I strongly encourage you to start working this way, so that you start with the pre-designs. But because this is a webinar, today I will start with an empty type of connection. First, most important thing is to set the steel grade correctly. Otherwise, if you do it later, you will have to take some extra steps. For the bolt assembly, because it's an empty connection, this is irrelevant, and same applies for the concrete grade. So I will click on create new project now, because I want to use a steel grade of S235. And now we have started the software. The first step is to create new member, and the first member you will always have to create it from here. So now I go to the hollow sections, and I go to the library of hollow sections. Usually the hollow sections that you need will be here under your favorites, but if you cannot find them here, you can go to all and find another lists of hollow sections. So I will go to the square hollow sections, and I will search in the list to find the first one, and the first that we will use will be 140, 145, okay? So it's all set, and then I will click OK. For the second section, you can remember, you can either create it from here, or you can do it by right-click, copy, and now we have the second member. Now you can see that both of them are overlapping, but I will change the direction of the second one, and now we have both of the members. So for the second member, we will use a different cross section, and you will have to go to the plus instead of editing, because if you edit the parameters, then it will automatically change the cross section of the first member. So I go to the plus, and then I go to the square hollow sections, and I will search for the second hollow section that we will use, and that would be 160, 160, and 5. Okay. Now we have both of our members ready, and the next step will be to align them. So my goal would be to create one straight line on the top of webs of both members, and to do this I will use this align that is in the newer versions in idea statica, and I will choose to align this member in relevance to this member. So I will go to member plate, I will change the view, and I will choose align plate, this one, and next I will choose related plate, this one. So let's see, we will have to choose the related plate again. Okay, so this looks better. Now we have one straight line on the top of both webs, and the last step would be to set the bearing member, and I will choose M2 to be the bearing member. So click here. So now we're finished with the members. The next step will be to do the operations. So I go to the operation, and then you can see here that there is a list of operations, and some of them might seem to look alike. Like an example, we have here beam to beam connection as well, but there are small differences between them, so always choose what you need. This one is one beam that is perpendicular to the other beam, and this one is the one that we will use today, and it will be two parallel beams. So I will click on it, and now I have to choose the bolts, so I choose grade 8.8 and I will leave to M12. Okay, so now we created what it seems to be the connection. Also we have the bolts in here. First I will adapt the thickness of the plates, so instead of 12 millimeters I will go to 10 millimeters. And in here there is an option to use welded, but we are not working with welded type of connection. I will leave it to bolted. For the dimensions, I will choose to profile, and to explain to you what to profile means, I will demonstrate that on the drawing. So I will put everything on 0 now, here 0, 0, 0 as well. And if I put a number in here, so the measuring will start from this line to above. And if I go to 75 millimeters, you can see that top means from the outer edge of the top web going outside. So this is the 75, and same applies with the bolts as well. So if I put 45, these bolts from this corner will move 45 millimeters. So I will put 75 everywhere, and also for the bolts I will do 45 everywhere. Okay, so now I have the bolts into the corners, and I have to do another set of bolts, so the bolts into the middle. For the bolts I can either do it with -115, meaning that this will start from this point, so it takes the coordinate system of the last bolt and then it goes below. Or if you want to start from the starting point, then you will have to do this separator, and then you will have to add a value. Let's try -70, and then this is another way of introducing these bolts. So this is how the bolts would look like, but you can see that right now we have one extra bolt that we don't need it, and in order to delete this one I will have to go to the editor, and then I will explode it, and under 6 I will delete this one and click OK. So this is the correct position of the bolts. Now you will notice that this will be locked, so here you cannot do any changes. If you want to do some changes again, you will have to go back to the editor, then restore this, and then you can do changes here. Okay. We also have to adapt the welds in here. You can see in the corner here, when I go on the elements, it says webs. So obviously we don't have any flanges. So for that purpose I will put the welds on the flanges under no weld. And for the webs I will do one-sided fillet weld with 5 millimeters. I think we're finished with this design, and now we will have to move to designing the ribs. So I go to operation, and now you can see that there are two ribs that look alike. One of them is called widener and the other one is rib. So this one is meant to be used for open sections like IP or HE sections, because the script will ask you for flanges, and because we don't have flanges we will have to use this one, and this is the rip operation. So I choose the rip operation, and I will first adapt it. So first I will start with member M1. So here is member M1, and I will make it related to, instead of a member, I will make it related to a plate. Okay, so you can see that here it is created. First I will adapt the sizes that I see in this view. So instead of triangular, I want to use a chamfered shape. Then the dimensions here will be 10 and 10 millimeters, and maybe I can adapt this as well. So the depth will be 100 and the width, let's take it 70 millimeters. So this is almost okay. So now I will go to this view, and you can see that there are a couple of extra more ribs that we will not use. First, to remove this, we will have to go to surface and select the lower surface, and next to remove the extra here, so I don't need the central one, I will have to work with location. But you can see that the options right now are front, rear, or both, and center, and we don't have, if I go to both, you can see that I don't have an option to work just with this and this. So first I will select the front. Now I have the front, and to do the other one I will do a workaround, and I will work with the repeat count. So I will put a repeat count of 2, and for the delta I will put a number of 115. And the last thing to do is to adapt the thickness, and we will work with 6 millimeter thickness, and for the welds I will work with 3 millimeter welds. So we are almost finished with the ribs. The last step will be to do an opening in here, so that we prevent intersections between the weldings in here. So for that purpose I will go to the editor, and I will do a rounding. For the corner I will choose corner 5, and because you can see that the rounding is in this direction, I will choose select the opposite, apply, and then OK. So let's agree that this is finished. So now I can move to the other ribs. I will simply copy this, and now instead of cross-section parts web 1, I will choose web 2. Then I again copy, and I choose web 3, and I copy again, and then I choose web 4. So we're finished with this side. We will have to move to the other side. So I copy this design, and I will select web 1, but instead of web 1 on member 1, I will choose member 2. Obviously you see here some information about possible clash, and also in here it is already visible that there is a clash. If I go to this view, we can see where the clash happens, and we can see that the reason for the clash is because we have selected the wrong plate. So if I go back to this operation, now we have selected plate A, but I will have to choose plate B. So now it seems better. Okay, I will again go to the solid view, and I will go in this section. Obviously we will have to adapt the geometry of these ribs. So instead of 70, I will put 50, and also the distance between them will be 135. So this is much better. Then I copy this again, and I will move to web 2. And for web 2 I will make them more wider, so it's 60. Then I copy this again, and I will choose web 3. So for web 3 I can go again with 70 maybe, yeah, and I copy this to web 4, and for web 4 I will have to go to 60. And we can conclude that we're finished with the design. This is a transparent view of the design, so you can see that there is no collision with the bolts and the plates. I will go again to this view, and now the last step would be to load the connection. So I will go to loadings, and I will create one load case. For this load case, we will load M1 with 100 kilonewtons, and that would be all. And like I said, so I go to connection, and I will have to choose the analysis type. So we will start first with the joint design resistance type of analysis. And I can run the calculation. This type of calculation, including also the stiffness calculations compared to the stress and strain type of calculations, take more time. And this is due to the fact that the software will do rounds of loadings. So it starts multiplying, and it's looking for the balance where it can find the factor. And when the software finds the solution, the calculation will stop. So for this type of calculation, we will have to be patient. And also, if there are more than one force and the connection is more complex, then more time it will take. So we can see that the software already found the factor. Now it's performing the last calculation. And usually when you run other types of analysis, you always have the default analysis, so the results for the default analysis, and that is the stress strain analysis. And also we will have the extra information for this type of analysis into the check. Okay, so we can see that obviously under 100 kilonewtons we have a lot of margin into the calculation, because everything is in gray, or almost everything. We just have these plates in green. And here we can see the percentage of how much everything is close to the failure. If I go to the check now, and here you can see that this is extra check that comes from the joint design resistance. And here we have the factor. So the factor is given in percentage, or 330%. Or if we want to work with the value, that is 3.3. So we have a margin of 3.3 under loading of 100 kilonewtons. Another information that we will have, it's here, it's located in here. So here we can see that there is 1.9% in the plates, and it's below 5%. Also, we can see that the welds are not close to 5% either, and by judging by these two, we can see that under the maximal factor, it's most probably that the bolts have failed. Here also we have a diagram, and from this diagram we can interpret of how ductile the connection is, and we can do that by watching how epsilon changes when the software applies steps of loads, and how the diagram goes, or what is the direction of the diagram, how steep it is. And because the software, when you run joint design resistance, will only check the failure of plates, welds and bolts, and there are some other effects, and they have unknown directions, so these effects are not taken into account. So that is why it is advisable to, when you finish this calculation, always take this factor and run, multiply your forces with the factor, and then run the stress strain analysis, so that you will be sure that that is the correct factor. And now we have 3.3. So obviously 3.3 is the border, or the limit where the connection will fail. So instead of multiplying 100 with 3.3, I will do it purposely slightly bigger. So let's take 340 instead of 330. And now I will change the type of analysis. I will go to the stress strain analysis just to see if everything is like expected. So this type of analysis, like I previously said, should be much quicker compared to the other analysis. And let's wait for the results. Okay, so now we have the results, and you can see that our assumptions that the bolts would fail were correct. We can see that the failure happened in these two bolts, and there is slightly more margin into the plates and into the welds as well. And also this example, because this is part, let's say, of a truss, I took one axial force, but the same thing can be applied to a set of forces. Like in example, we can have one axial force, and also we can have a bending moment, and we can have a shear force, and then we can ask the software to run analysis and to give us a factor. Then and if we multiply all these forces with this factor, then we will have again the same information about the failure of that connection. So it's applicable also not just for one force, but with a set of forces as well. So this is all that I have prepared for today's video. I hope you enjoyed it, and see you in my next video. Bye.